So if you remember the derivatives from Calculus 1, you have a function f of x, and then we said that the derivative at a point x naught, y naught. Oh, sorry, just x naught. Let's make that x equals x naught. It's given by f prime evaluated at x naught. Do you remember what the definition of a derivative looks like? Limit as something approaches 0 of f of x naught plus h minus f of x naught all over h. So that's a definition, and we found all kinds of shortcuts and nice ways to find derivatives of things, the power rule, product rule, quotient rule. We even went as far as diving into the chain rule. But really the definition of the derivative is a limit. And the derivative, as we saw it back then, turned out to be the slope of the tangent line. And before we get to the tangent line, in finding the slope of the tangent line, we found the slopes of the secant line. And then we let h get closer and closer to 0 so that we get these points closer and closer to 0. And so these tangent lines, these secant lines, will eventually start to look like a tangent line. So that was our idea back then. Now we got to bring this up to 2 variables and an output variable, which brings us to the 3 dimensions. So now we're dealing with a function, z is equal to f of xy, where f takes a 2-point input or a 2-vector input and gives it a scalar output. And then we're interested in finding derivatives of these things. So I think what we'd like to do is we'd like to stay with this idea of a derivative as a limit as x approaches something. And so what we're going to come up with is, let's try to look at it from a graphical point of view first. What we're going to come up with is a way to scale down our 2-input into a 1-input. So it will scale down our 3 dimensions into 2 dimensions. And see how things would look like from there. And so let's learn to start identifying portions of my standard 3-dimensional surface graph like this. This is z is equal to f of xy. That's the surface. and then I have a point x naught, y naught on the domain. And so what is my actual point on the surface? Would you know what that is? So that's the z component. That's the height, right? So I would still need my x naught, y naught for my x and y components, and then the z component is f of x naught, y naught. So again, you'll see this information a lot. The same looking picture with the same labels. Okay, so what we're going to do to start trying to approach derivatives is we're interested in looking at derivatives in this two-dimensional sense. And we have derivative in 3 dimensions. So what we're going to do is we're going to fix one of the variables. So I have x naught, y naught. What I'm going to do is maybe I'll fix what if I were to draw a plane that looks like this, what plane is that? It'll be parallel to the YZ. So what exactly is that equation of that plane going to look like? X equals what? X is a fixed number. In this case, we'll just call it x naught, because that's where it's passing through. That's the x value. So this is the plane x equals x naught, which is parallel to the YZ plane. And if I focus on just that, looking at it flat as if I was looking at the YZ plane, what I would get would be some corresponding curve that looks like this. Do you agree? And so what I have here is a y naught value for my x naught that has been fixed. So what I would like to do is try to imagine how I can define a derivative here at that point. So what I'm saying here is I'm fixing my x value to some number, x naught, and then I'm finding the derivative with respect to y. We could substitute x naught into the original function. So z is equal to f of x naught y would give me a fixed number for x naught, and then now this is just a function of y. Now I could just take the derivative of that with respect to y. So more formally, I'll put the notation here in a minute, and there'll be several notations for this. This would be, you know, if we do that limit thing business that we did over here with the tangent lines and stuff, we can pretend that we're letting h go to 0, and that's a change in the y direction only. because x naught was fixed, but y is changing, and so this is where I'm bringing that h closer to 0. Okay? So what I have here is the derivative of the function f with respect to WRT with respect to y. And the notation for this, or one notation that we will be using, is we'll take their f and put a subscript. Instead of putting a prime here, a prime doesn't really make much sense because I have two variables, x and y, to deal with. So I have to specify what I'm taking the derivative with respect to. Oops. And in this case, I'm taking the derivative with respect to y. So one notation for us will be putting a subscript to let people know what derivative, with respect to what variable we're taking the derivative of the function. Okay? So this would be like this graph, and then I'll get a tangent line over here. So what does this derivative tell me? As derivative, back in calculus, a derivative told me that's the slope of my line. Slope is a little bit more difficult to look at when you're on the surface. So let's be more specific about the slope. What does this f sub y tell me? Slope of the line. It's not quite on the yz plane. No. Slope of the line, it's the slope of this line intersected by this plane where you're fixing x constant. So it's the slope of that line in the y direction. Okay. So let's try the other way of doing this. It's a little bit more difficult to visualize, but let's see how the drawing skills are. Has your drawing improved since the beginning of the semester? This time, let's look to fix the y value with this plane that would eventually cut the surface right there. All right, so how does that look like? If we look at that plane, what plane is this, by the way? It's y equals y naught. That's parallel to the xz plane. So it's not the xz plane unless y naught was equal to 0. If y naught was equal to 0, then it would be exactly the xz plane. but it might not be. But at least we know it's parallel to the xz plane. So if we look at it from like the positive y-axis, we can see the xz plane in the background. And then we have a graph of that. So this point over here on this y equals y naught will reference that as some x naught value. And then we want to find the slope of that line again. Maybe let's use purple for that one. So what is this? This is fixing your x, this is fixing your y naught. Z is equal to f of x y naught. So y is variable, y is varying, y changes. And so if we take your h, run it along the y-axis, or along the x-axis, your x is changing. So if you run that along the x-axis, you can find your derivative the way we did before, and we'll call this f sub x. And that's going to be the limit as h approaches 0 of f of x naught plus h y naught minus f of x naught y naught all over h. And this is the derivative of f with respect to x. AJ?
So if you want to actually take the general derivative, not at the point, with the x naught, just the x.
Yeah. So if you want to take the general derivative, you can just replace all the x naughts and y naughts with just x and y's. This would be the slope of the line in the x direction. So that purple line over here would be in 3 dimensions. It would look like this. Pretty cool looking, huh? Okay. All right, any questions? Yeah, that picture. I can't turn it because I just drew it. But if we were to draw this, we could see it being turned around and stuff. But for us to be able to draw it, we would need information about these lines. These are lines. They're tangent lines, tangent to the surface. But there's, if you look at a surface, how many tangent lines would be tangent to a surface? Yeah, these are 2 lines out of an infinitely many possible tangent lines that would be tangent to a surface at a point, at one single point. So what would be a better way to describe something tangent to a surface when we're taking a look at functions like this? Tangent plane would make a little bit more sense, right? You guys will talk about that tomorrow. So I think we first need to generate a way to find out these lines and then eventually the plane. And once we do that, we can begin drawing this on a computer program so that you'll know what I'm typing in when I'm typing it in. But right now, we'll just have to stick with this business. Bunch of scribbled mess. All right, so that's the graphical point of view of derivatives. Let's take a look at, I want to do a numerical point of view of derivatives, but before we do that, let's talk about notation. Because the notation is kind of strange. So we first use this f sub x as the derivative of f with respect to x notation. So this is kind of equivalent to the prime notation that we use in calculus. And there's another notation for derivatives in calculus 1, right? Leibniz notation, df dx, dy dx. So there's something similar here as well. So you can't use the d, though, because the d stands for a derivative with respect to one variable when you know that you're dealing with one variable. So what they do is they change their d a little bit. And they change the d to make it look like this. It's like a curvy d. And this is saying the partial derivative, because you're only taking the derivative with respect to one variable. So instead of saying derivative now, let's be a little bit more precise with our words. This is called the partial derivative. A derivative of f with respect to x. It's a partial derivative because your function has more than one variable that you can take the derivative with respect to. And with that, you need to say that you're not taking the whole derivative, you're taking a partial derivative of it. Later on, we could talk about combining these derivatives into one big derivative that we can call, I don't know, the total derivative of something. But for now, we're talking about partial derivatives. Okay? So this is our partial derivatives. It seems really easy to just write f sub whatever the variable is. And for most cases, we'd want to use that. So why do we bother introducing this notation with the curly d's? The reason why we do that is because there's a lot of formulas out there already that has been traditionally written with these partial d's. And so a lot of those, they're called differential equations, but they're differential equations with partial derivatives, so they're called partial differential equations. And there's a lot of those partial differential equations that are written with this curly d notation. Plus it looks kind of cool, the curly d, doesn't it? It's almost as cool as the integral sign. So the integral sign would be a very cool tattoo to have, and that was initially going to be my first tattoo, as an integral sign down the side of my leg here. But I didn't get it. I got Mickey Mouse instead. When you have kids, you start making weird decisions. No, I don't do Mickey Mouse. All right, so that's a notation for derivatives, and we'll compute derivatives. Well, let's compute derivatives now, since this is the easy part. Remember how in Calc 1 you kind of struggle through finding limits of things, and then all of a sudden the teacher told you that there's a shortcut for these derivatives?
Go straight to shortcut.
Yeah, so we'll do shortcuts, but we'll need to backtrack and take a look at derivatives where we're looking at a numerical table and stuff like that as part of the homework. But in general, let's take a look at some simple examples of derivatives. So, I don't know if we start with, what's this function look like? What? What? No?
No, it's not three dimensions.
This f of x is actually equal to z. Z is equal to x squared plus y squared. What is that? Oh, man. It's a circular paraboloid. It's a paraboloid. You guys are just kidding, right? Just throwing out all kinds of weird names that were all incorrect and just to throw me off my game. All right, this is a paraboloid. Let's take the derivative of this. So what's fx equal to? So the point is, remember, you're going to treat the other variable as if it were constant. So you focus on the x as a variable. So this is 2x. And what's the derivative of y squared if y is constant? 0. So that's it. We're done. This is the derivative. All right? So that's our little warm-up. I'll keep using f. All right, let's take the derivative of this. Let's start with respect to x. What's the derivative of the first term with respect to x? 1 times the constant, e to the y. Right?
Which is either, okay.
What's the derivative of y times e to the x with respect to x? So derivative, remember, y is a number, but e to the x. Y e to the x. Did I jump too high from a really simple example to a... Do we need Mickey Mouse steps? So here's a trick. If you see you're taking the derivative with respect to x, treat y, pretend y is a number, like call it 5, not 1, because 1's just going to mess you up. So call it 5 or 17 or negative 32. Just pretend it's a number and then take the derivative of it, and then put those numbers back, or put the variables back in place of the numbers that you used. Okay? All right, let's go to the next one. So there's a product rule here. Now there's 2 x's in a product. So derivative of the first times the second plus the first times the derivative of the second. So this all came from this. What's the derivative of the last one? 0. There's no x's there, right? Everything is a constant. So derivative of constant is 0. Good? So how about the next one, fy? What's the derivative of that first? Now that we've done fx, this shouldn't be too bad, right? What is this one? So x is a constant. The derivative e to the y is e to the y by itself. So this would be x times e to the y. So y is the variable. E to the x is a constant. Pretend it's 5. Y times 5. The derivative of that is just 5. So that's e to the x. The derivative of this next one. There's no y's in it. So it's all constant. And then the last one is your product rule. Yeah, e to the y, e to the y. Okay? All right, while we're on this page, we might as well talk about the derivative of the derivatives and higher derivatives. So there's really nothing to higher derivatives except for the notation. So let's label a higher derivatives little subsection here. So I don't have to start a new page. So higher derivative, what is a second derivative? You're just taking the derivative of the first derivative, right? So one way to denote that is this is your first derivative, fx, and you're taking the derivative of x with respect to x or y. So it'll be called fx x. Let me write it like this, fxx. And so when you do this, this makes sense, right? You're taking the derivative with respect to x2, and then take the derivative with respect to x again. No, they're both the same size subscript. No, that was a good question. I always make a big deal back when I used to teach logarithms, pre-calculus. Oh, can't imagine teaching pre-calculus anymore. But those logs, you know how they become subscripts and along the same lines as superscripts and stuff? So I always have to teach logarithms with this. Do you know what this is? You know when you're in grade school and then you're learning how to write your letters? Right? And so it's important to figure out whether something's a superscript, a subscript, or along the same lines. So when you say log base 2 of x to the 5th power, you know where the 2, the x, and the 5 are. One's a superscript, one's a subscript, the other one's along the same lines. And so people have a hard time with that. You guys have passed that, right? You guys have that was a good expression, right? So let's take the derivative of fx with respect to x. So the derivative of e to the y with respect to x is what? So that's 0. That's gone. A derivative of y e to the x with respect to x is what? It's still the same, y e to the x. Derivative of e to the x with respect to x, still e to the x. And then the derivative of this one. So e to the x plus x e to the x. Yeah, I kind of did the product rule here. Maybe I should have done it on another page. Okay. I suppose we can simplify this if we really wanted to, but I don't want to. So let's move on to taking the derivative. Let's take the derivative of fx. This time let's take the derivative of that with respect to x, or with respect to y, since we already took it with respect to x. So this one is called fxy. Right? Makes sense. So now that tells us that we need to look at fx first. and then take the derivative of fx with respect to y. What's the derivative of e to the y with respect to y? E to the y. What's the derivative of y e to the x with respect to y? E to the x. What's the derivative of e to the x with respect to y? And the derivative of x e to the x with respect to y? Okay. All right. Let's do a couple more until you get bored. Let's take the derivative of fy with respect to y, so we'll call that fyy. So the derivative of x e to the y with respect to y. X e to the y. The derivative of e to the x with respect to y. 0. That's 0. Derivative of e to the y with respect to y. E to the y. And then the derivative of the last one. E to the y plus y e to the y.
So my question is, there's another y e to the y at the end of that. Why are we not also taking the derivative?
Because the derivative e to the y is e to the y. So it's the derivative of the first times the second plus the first times the derivative of the second for this thing. Right? So the derivative of y is 1 times e to the y.
But then isn't there another e to the y missing?
Is it this one? Oh, this e to the y is right here. Right? That came down here, and then this expands to that. All right, now let's, one more. Let's take fy and then take the derivative of that with respect to x. So what would we call that? fyx. So the derivative of that will look like we need fy, that's this, with respect to x. The derivative of the first thing with respect to x is e to the y. Derivative of e to the x with respect to x, e to the x. Derivative of e to the y with respect to x, 0. And the derivative of that last one with respect to x, 0. All right, that was fun. Yeah.
So, taking the derivative of the derivative has like acceleration.
Yeah.
What's the purpose of taking the derivative with respect to x of that y? What does that tell you?
That tells us how your derivative is changing with respect to how your derivative with respect to x is changing with respect to y. So it's like, yeah, that's what it is. All right. It doesn't quite make a plane. The second derivatives, though, they would describe concavities, which we probably won't touch on too much. You guys notice anything?
They're equal to each other. We have
So it turns out that this little fact over here isn't just a coincidence. It actually happens for nice functions. And fortunately, we'll be dealing mainly with nice functions. We call this mixed ordered partials. Because they came from the x and the y, and so they are mixed. And it turns out that if you're dealing with a nice function that doesn't have any weird discontinuities or weird limit does not exist business, that your mixed partials will always be equal, right?
I was just going to ask that if this is going to be true for our...
Yeah, so for we would probably only explore things just for the sake of exploring where the mixed partials are not equal. We'll probably introduce some weird functions where this isn't true. But in most cases, it's going to be true for us. Yeah.
There's some pattern to the way it works, like
Yeah, something about continuity. It's the continuity business. All right? All right, so that's good news because the notation, I'm still not quite finished dealing with the notation. When you have fxx, more notation, you can write that as a partial of f with respect to x that happens twice. And so just like the second derivative Leibniz notation, this is how we would write it. I mean, where does this come from? This comes from taking the derivative of f with respect to x once, and then taking the derivative of this again with respect to x, right? And so that's why they have this d squared f dx squared notation, because they're assuming the dx squared is like a quantity. It's not really a quantity, it's an operation symbol. So that makes sense for the xx and xy, but notice what happens when you have xy, when we start looking at the mixed partials. This is taking the derivative of f with respect to x, and then from there taking the derivative of that with respect to y. So if you put it together, this is d squared f, and then dy comes first, and then dx comes second. So notice how in the Leibniz notation for partial derivatives, those two are now backwards. Here we see xy, here we see dy dx. So just remember, when you're reading the Leibniz notation, you're reading from right to left. You're taking the derivative with respect to x first, and then with respect to y. You're taking the derivative with respect to x first, and then with respect to y. Okay? So, like I said, because of our special formula, there's a name for that. I can't remember what it is. Because these two are going to be equal to each other anyways, this isn't going to matter how we take the derivative with respect to first, right? So that's the good news. The bad news is that we could take this to higher dimensions and take the derivative with respect to x, y, and z in that order, in which case the order will be important. Okay? So it's important to read your notation properly. Just remember Leibniz notation, you're going from right to left. Take the derivative with respect to x first, and then with respect to y. In the regular subscript notation, we're going from left to right. So in other words, if you have w is equal to f of x, y, z, a function with 3 variables, my f of x, if I decide I want to take the derivative with respect to x first, and then with respect to y, and then with respect to z of this function, then what that means is that I'm actually taking the derivative of my function with respect to x first, and then I'll take the derivative with respect to y second, and then I'll take the derivative with respect to z last. So that means my notation will look like it's backwards from the other notation. Yeah?
Is there an equivalent to this? You know how in the mixed ordered pairs, is there an equivalent to 3 dimensions?
Probably, but I haven't really explored that, so it's not going to be important for our class. Okay. All right, so just a bunch of weird notation, that's all. Let's take a look at partial derivatives from a numerical point of view, as seen in your homework. I think your homework is a wind chill factor, so I'm kind of tempted to use the wave heights, open C. So let's do that one. So remember, we discussed the idea of making a table, a two-dimensional table to describe your function in 2 variables, where the values inside a table would represent like the z, the heights of these things. So the wave heights h in an open C depends on the speed of the wind and the length of time that the wind has been blowing at that speed. So values of the function h is equal to f of vt are recorded in feet. That's what h is. H is in feet in the following tables. What are the meanings of the partial derivatives dh, dv? So this is your function. So instead of calling it df, dv, they call it h, dh, dt. So you'll get used to the notation eventually. So dh, dt, or dv is what they want both, but let's do v first. What's the meaning of this? Let's try to use words to describe this. What's dh, dv? Okay, this is the partial derivative of h with respect to v. But in terms of h being the height of the wave, v being the velocity of the wind, and t being the length of time that the wind has been blowing, what is dh, dv? Yeah?
How much the height changes, the change of height over the change in wind speed while time is constant?
So h, yeah, so the dh, if you look at d as, if you replace the word d with the change in h, the change in height with respect to or as the change in velocity velocity is a speed, as a change in speed of the wind. And there's one more thing we need to add on to this, is that when we're looking for the derivative of things, we're looking as something changes, as something increases a little bit, right? So a slight increase. So change in speed of wind increases. So that just tells you that you're going in a positive v direction. Okay? Does that make sense? So what we're saying is that we're not saying anything about time, or you can say time, let's fix time here. As the speed changes, as the wind speed changes, how much is the height of the wave going to change if you fix time? And so dH dt would be the same thing, the change in the height of the wave as the time goes forward. So what you're saying is that you're fixing the wind speed, you're fixing v, the wind speed, and then you want to know how your wave, how the height of your wave is going to change as time increases. All right? So now let's answer the part B. Estimate the values of FV of 40, 15 and FT of 40, 15. So we just have to remember that 40 is the velocity. That's the first variable. Velocity 40, 15. Okay? So one estimate of this would be to see how it changes as you go forward with respect to v. So as the wind velocity changes, we want to know, as the wind velocity goes from 40 miles per hour, something, to 50 miles per hour, how is this wave height going to change? So FV of 40, 15 would be approximately equal to the change in height, right? Change in height over the change in speed increase. So it goes from 25 to 36 as you go from 40 to 50. This is 11 over 10. Is that what this is? So in general, I'd be good with this, but the book and the homework apparently will be want you to get a better approximation. And what I'm doing here is I just see what happens from 25. If I move forward, how does that look like? Okay? But if you look at that from a graphical point of view, if I go forward, how does that look like? I'm only looking at the slope of this line over here. So what might be good is that check yourself going backwards as well to see if you get a better average if you take the two. So what we're going to do is make another approximation of what happens when I go backwards. How does that change? So the change in height, again, using the table, is 25 minus 16 divided by, and then here I have the change in from 30 to 40, so 40 minus 30. And then I'm going to get a value for this, which is 9. So these are good estimates of the derivative, but if you want to get an even better estimate, why not take the average? So better estimate So take the average of these two things. So your FV of 40 comma 15 is going to be the average of these two things. So if you take the average, you'll get a better estimate of what's happening exactly at that point. Not just going forward and not just going backwards, but between the two, you'll get a better idea what's happening exactly at that point. Okay? Does that idea make sense? So the same idea goes from 25, and you change your time going positive from 15 to 20, and then you change your time from 10 to 15 and see how this changes. So I think that should answer one of your first questions in this homework set, 14.3. Okay? So I won't do that one. I'll let you figure that one out. Let's see if we can answer this last question. What appears to be the value of the following limit? This is t. As t goes to infinity, so what are we following here? Are we going to the right or are we going down? Which one is t? T is the one up here, so going to the right. So let's look at values of t here. This remains at 2. This went from 4 to 5. This went from 9 to 19, 33, 48, 50, 67, 69. So I guess the thing to look at is the change. We're looking for the derivative of h with respect to t, and so how it's changing. So the change here is from 4 to 4, the change is what? From 4 to 5, the change is 1, 0, 0, 0, 0. So there's no changing here with a low wind speed. Over here, it changed. Let's go down over here with a high wind speed. 24 to 37. What's the difference there? Is that 13? So there's a 13 feet change in wave height. This is a 10, 7, 8, 5, 2. So what seems to be happening here, the difference between the wave height values. So remember the dh is a change in height. Over the change in time. And we're seeing that the changes between the heights as your time goes along tends to what? Seems to, they tend to be less and less. So it looks like that limit is going to approach what? So it looks like the limit is going to approach 0. Okay. Any questions? So what you need to do is you need to look at, first of all, you need to understand that on this table that the values in the body of the table give you the output values of the function. In this case, it's the height. And then the values in the first row and the first column are the values for the two variables that you have, and you have to know which is which. Okay, so to read this table, you say, if I want to find out my height when the wind speed is 40 knots, and I have the wind blowing on this for 15 hours, then the wave height is going to be 25. And so the derivatives deal with how it changes if you go move along the x or move along the y. Yeah?
Is this how people like determine causality and correlation and stuff?
No, they use, for cause and effect relationships between things, they have to do an experiment. So they do statistics where, so these are just probably recorded facts, and they I don't know about the cause-effect stuff, but.
Well, because like the only reason I say so is that like the height is not looks like doesn't have anything to do with the amount of time that passes, but it does look like it has stuff to do with the wind speed. You know what I mean?
Yeah, but it might have something to do with the height. If this is an hour, so if we cut it down to like minutes, it might make a bigger difference then. And for some things like this, instead of actually coming up with a function, which somebody probably can do, they could probably come up with a function of several variables here with sines and cosines or exponential functions. They just recorded some data and put it in a table like this, and then we're going to go by this for now. All right, let's take a look at your homework, see what else we should think about. There's a wind chill factor question. Oh, I need to do graphs. Bummer, running out of time. Let's do this problem real quick. And so let's take a quick tour of dealing with contour maps. So we want to know at 2, 1, this is my x, where's my x? This is my x-axis. 2, 1 would be over here somewhere. That's my point. If I want fx, right, I want to know what happens when I move along the x-axis, and I want to know what happens when I move along the x-axis from both going forward and going backwards and take the average of the two. That will give me my best estimate. And so to do that, these level curves tell me my change in height. So this curve over here has a height of 6, has a height of 8. So if I'm standing, according to my map, my compass, if I'm standing at x is equal to 2, y is equal to 1, how high am I? I'm at a level 10, right? So if I want to change my height, if I look at my compass, my map, and then I move along the x direction, we'll call that going east. If I move east, according to my compass, after some distance, I'm going to be at height of 12. And so we need to estimate what this distance is. So I'm going to go change in height, change in f, is going to go from 10 to 12. And then my change in x is going to be however long this is. It's not quite 1. I didn't go from 2 to 3. I went from 2 to 2.5. I'd go a little bit further out. Um, 2.6 from 2 to 2.6. So I was standing here in my x going from 2, and then I moved 0.6 units. And so I would do the same thing coming from the other side, another change in f over change in x, where I went from 8 to 10, and then my height went from something to 2. And then this would be about, what would you say this is? What? 1.2 maybe? So you get values for that, and you take the average, and that would be a good candidate for your derivative of the function with respect to x. Okay? So this is, if you translate this reading the graph from reading the table, it's kind of like the same thing. You're trying to figure out how your height changes, how your function changes with respect to how one of the variable changes. And so to figure out with respect to y, you do the same thing, except you're climbing north-south instead of east-west. And then sometimes some of these might actually be going down, so you could tell whether you're going up or down. All right? I think that's it for today. So good luck with your homework.